Hi, Roy and Beaumont here. We're going to talk quickly about simple linear regression and how to carry it out in SPSS, R Commander and R. You can find details on my website along with a detailed PDF explaining this in much more detail with screen dumps, etc. Right, there are 8 steps really to consider when carrying out a simple linear regression analysis. Step 1 is always to plot the data. 2, we add the regression line. Remember, we're talking about minimize the vertical squared residuals here, and we're talking about a straight regression line. Then we consider adding a confidence and prediction interval to the line, which shows us how typical our points are to the predicted line. Then we obtain the usual model statistics, which consists of the parameter estimates and the ANOVA table, details below. Then we obtain the various influence statistics. This shows us which values in our data set particularly influence the estimation of the parameters and which values might be very atypical. We then consider all the align assumptions. We'll come back to that in the next screen, but that is to do with an aspect of statistical validity. Are actual results valid? 2 of these line assumptions are analysed graphically in the output using regression diagnostics. We can carry out a visual inspection to see if the equal variance exists over all the range of x values, and also we consider if the residuals are normally distributed. Again, we can assess that graphically. There are also 3 important dangers we need to consider when carrying out regression, another aspect of statistical validity. First one is the range. Are we extrapolating beyond the sensible range? We're considering ages of 120 or something when we're looking perhaps at only 20 to 40-year-olds, or are we looking at pulse rates that are negative? Subgroups, we might be clumping together males and females, which might be very different. They even might have different regression lines but go in totally different directions, which would result in us probably having insignificant regression. And we must remember that although the mathematics underneath simple linear regression is to do with causation, what we're actually only doing is looking at correlation. And actually, if we want to infer causation, does the independent variable really cause a change in a dependent variable? We need to consider additional criteria, which are called the Bradford criteria, developed in the 1960s. Again, go to my website below, it gives full details of the Bradford criteria for considering causation. Just one quick word about the line assumptions. Line stands for 4 aspects of our data. First one is linearity. We're only really considering a straight line relationship. You can see that big black straight line. We're not considering curved regression lines, straight ones. Next thing is independence. We're considering that each y value is independent of any other y value. Thirdly, normality. If we take a particular x value, we might have more than one bits of data related to that same x value. If we've got that, we expect that our estimated value on our regression line consists of normally distributed data for any x value. This also goes for the variance, the e in the line assumptions. So we're considering that for any x value, the variance of this normal distribution we're considering does not vary. It doesn't go up or doesn't go down as the x values go up and down. It stays the same. Let's get on with doing it. The example data set we're going to use is that concerning lung cancer mortality and cigarette consumption. So we have here in the second column lung cancer death rates per million for various countries. Then we have in the final column the cigarette consumption in 1930 per adult. So if we go to SPSS, first stage was to plot this data. So we go to plot graphs, legacy dialogues, scatter dot. That was legacy dialog, scatter plot, then click simple scatter and then define button, and then in the top we put the rate of lung cancer, then the x-axis will have the cigarette consumption. Click OK, and here is the output, very simple scatter plot, and we can see the cigarette consumption for adults goes up, the incidence of lung cancer goes up. This is just a correlation, remember we're talking about, not necessarily causation here, unless we look at our Bradford Hill criteria and see if they're fulfilled as well. Right, now we'd like to add a confidence interval and a prediction line in SPSS. So we just click on the chart, which brings up the chart editor. Once in the chart editor, then we click on this option that says add fit line at total, add fit line at total. If you can't see that little icon, you can go to the elements option, and we've got the same option there, fit line at total. Click on that, and it brings up a dialog box where we've got different types of fit method. It's already chosen linear, which is what we want. Then we have options here of different types of confidence interval. We have a mean and individual. A mean is a typical one we use, which is called the confidence interval in usually most stats books. Individual one is also called the prediction interval. So we'll choose the mean and apply, and there are our confidence intervals. Close that, then we carry out the same process again, but this time choose individual, which is the prediction interval, click apply, and we can see the prediction intervals are much wider than the confidence intervals. Details why this is the case and what they both mean in my PDF handout on the website. To carry out a simple linear regression, we choose the menu option, Analyze, Regression, Linear. Analyze regression linear, and we come up with the usual dialog box. The dependent variable, the outcome variable in this instance, the result, is lung cancer, and we think what affects lung cancer is cigarette consumption. Think of the input output if you're thinking of a causal model. If you're thinking of correlation, just two values, don't really matter which way around they are. We can choose various options here. Statistics, we can ask for confidence intervals, which we will want. Okay, continue. Options, we don't need to worry here because it's simple linear regression, we can ignore the options. Bootstrap, this is to do with developing robust estimates of the standard error, the standard deviation of our parameter estimate. So we click on Bootstrap, we can select Perform Bootstrap and ask for a robust estimator for our standard error for our parameter estimates. So I click Continue, and we'll be able to compare that with the traditional normal distribution method of obtaining the standard error of our estimates. Also, there's a Save option here. Notice that. Click on Save, and here is where we find all our influence statistics and various other things. Notice that SPSS divide them up slightly differently to other stats packages. So we've got distance measures here and influence statistics here. They tend to get swapped around in different stats packages. Click OK. It may take a minute or two to run the bootstrapping samples. I think we asked for 500, but don't worry, it'll stop after 5 minutes. There's an option for it to do that if there's a problem. So here are our results. Typical output. So we have R value there, 0.764, R square value, coefficient of determination, typical ANOVA table, and the parameter estimate value here, B, beta, the standardized value. Notice, because this is simple linear regression with one predictor, beta value 0.764 is exactly the same as the correlation, 0.764, and a 95% confidence interval. This is a traditional one worked out by normal distribution theory, 0.124 to 0.358. If we look down here, here are the bootstrapped versions. Notice no difference for a parameter estimate 0.241, but notice the confidence interval, because it's based upon the standard error there. Traditionally 0.124, that's 0.115, and 0.358 there is now 0.342, so slightly different. Also notice that the significance value is higher for the bootstrapped method. Looking back at the dialog box we just used for linear regression, I mentioned about the save option. We can select various values here and save them into a data set. Say we wish to save Cook's distances and unstandardized predicted values and unstandardized residuals, and click those. And also we can choose the standardized BF betas if we wish. Click continue, say OK, and here are our results. I must mention that I actually took off the bootstrapping option to run these. You can't run bootstrapping and ask variables to be saved to your data set at the same time. We can use some of these additional variables to check out the assumption in line, that is, that there's equal variance for all x values. It's got a long name if you look in my PDF handout, which I won't try and pronounce now. Right, so to do this, just simply go to Graphs, Legacy Dialogues, Scatter, Simple Scatter, and select Define. And what we're going to do is compare the residual value against the predicted value. Click OK, so there is no real funnel effect. It's usually better to look at the standardized versions, and you can do that very easily in the analysis. When we carried out the analysis, if we go analysis, regression, linear again, and if we actually look at the plots option here, you can see we've got various values here we can put in. And if we notice there that x resid is the standardized residual, so we could put that in, and the standardized predicted there, x predicted is there, and we can say continue, make sure we've turned bootstrapping off, which we have done, OK, and there are regression analysis again, but there's a standardized residual against a standardized predicted value. And it definitely looks like a sky at night rather than a funnel. To assess the normality of the residuals assumption, we can do that several ways. We could actually plot the residual values there, just do a histogram and see if it looks normally distributed. Probably better to use the standardized residuals to do that. Another way is to actually, when we carry out the analysis, we look back again at the linear regression box, you'll notice there's a plots option here, and in the plots option it says a normal probability plot. If we click on the normal probability plot and remove everything else, say continue, this time in our output we obtain here a chart which has a line running along it, and that line is basically telling us where we'd expect the scores to appear if they were normally distributed. That is the standardized residual scores. And we notice most of them fall upon the line. Again, details in my PDF document, but that looks fairly good to me. So what have we achieved? We've carried out simple linear regression in SPSS. We've plotted the data. We've added the regression line. We've added confidence and predictive intervals. We obtained the model statistics. We obtained some influence statistics. Details, as I say, in my website below. We considered some of the line assumptions, which is a part of statistical validity. And we considered the regression diagnostics. We looked at the equal variance over the range of the x values assumption. We also looked at the normal distribution residuals. To find out more details, as I say, look at my notes. We didn't really consider the dangers of our little regression model we were looking at, smoking, but again there's a lot more details in the material on my website. Next time we're going to be looking at carrying out the same analysis in R Commander and R.